welcome to episode 8. Today we're going to be talking about air resistance. So, let's think about air resistance. So we have some particle, and it is moving some velocity, right? And it has, obviously we know it has the force of gravity acting on it, but now we're going to want to consider, normally we might think, oh, what's its motion? But now I'm going to ask you to consider this drag force, right? This force pulling it back. And we're going to try to think about what this force is and derive it. So first thing we're going to do, F of D. We know a few things here. So what is F of D? Well, first of all, this force works when we have some fluid. If we have some object moving through a fluid, just a bunch of particles, right? This drag force is the force that these particles exert on our object as it is moving, right? So you can think about, as you're moving, you stick your hand out or stick your head out of a moving car, right? You're going to see some wind, right? And the faster you're going, the faster the car is moving, the more particles are going to be hitting your face. So the more force is going to be exerted onto your face from all those particles. So we know that Fd is going to be some function of your current speed. And we also know that is in the negative direction of the velocity, right? So this is some magic function. What is it? We don't know. So let's try to think about this. We're going to make this assumption here that this function is continuously differentiable along with velocity, and that it has at least a second derivative. Okay, and that's a reasonable assumption to make when we're thinking about, continuous linear motion. So what can we do with that? If we assume that that's true, so assume continuous and differentiable, right? Under the right assumptions, well, we can assume that f of v, therefore f of v has a Taylor series, right? So let's take that Taylor series then. We're going to expand that. F of v is approximately equal to f of 0 plus f prime of 0 v plus, and obviously this is going to be Taylor series with the c equals 0, or it's Maclaurin series, plus f double prime of 0 over 2 v squared, and then I am going to cancel all the other stuff, right? We don't care about that. So now that we've got these points, right, what are we going to do with these? So obviously we can't take f prime because we don't know what those are, right? You can't even take f0 because that requires us to know what f is. But we can make some simplifications here. So f of 0, this is equal to 0 because we're not moving, so there's no drag. Now f prime of 0, I'm going to call this b, and f double prime over 2, I'm going to call this c. So we can split up our velocity into f of v is equal to bv plus cv squared. Right. So what is that? Right. So we have this, and what are is b and c? So these are going to basically break this force into two components. One is the linear and one is the quadratic. And these are related. These are both basically define sort of two different motions of drag. So obviously quadratic drag and linear drag. And so if we graph these, which is what I'm going to do next, we find, okay, here's Flin. Here is F quadratic. And then this is going to be both of them. So it's linear up until some point where it becomes quadratic. Right? So there's some sort of cutoff where F quad becomes significantly stronger to F linear. And if you remember, this is a function of velocity. So we have F quad over F lin is CV squared over B. V equals C over BV. If this ratio, FQ over FL, is significantly greater than 0, F quadratic dominates. So we can basically ignore Flin. We can ignore linear drag. Otherwise, if this is, if it's equal to 1, use both. And if it's significantly less than 1, use linear drag. So so this B and V, obviously these are still unknown constants. And there's a few ways we can get these. So B and V can be determined experimentally. Maybe run some experiments to determine this. But in general, they're related to this thing called Reynolds number. Reynolds number, and that's written R is equal to dv rho over eta, and this is the density and viscosity. And Reynolds number is related to both of these, but this linear term is related to sort of the viscosity of our object, and this is related to the density, right? The density and cross sectional area of impact. So we have some ball, right? We're going to have some area here, and we're going to have particles and stuff colliding, right? Okay. So F linear, if we want to expand this out just a little bit more, for a sphere, we have F linear is equal to 3 pi eta dv. For a, I'm not going to derive these, but this is a thing called Stokes' law. Right? And so eta is the viscosity, and this d is going to be the diameter of a sphere. And F quadratic, on the other hand, is equal to some coefficient over 2 rho this cross-sectional area squared v squared, right? So we can do some simplifications here. So for a sphere, B is equal to beta D, and C is equal to gamma D squared, and beta is more or less 1.6 times 10 to the negative 4 Newton seconds per meter squared, and gamma is approximately 0.25 Newton seconds squared over meters to the fourth. And so for a sphere, or better yet, linear drag, I messed that up for. So drag on a sphere is going to be F of D is equal to beta negative beta V minus gamma D squared V and then V. And if you're not sure what happens here, remember, notice this V hat. So V squared V hat is equal to V this, because from the identity V hat is equal to V, or our V vector is equal to V hat. And so that's what happens with this guy, with both of these. So next thing we're going to do is I'm going to look at actually solving some problems with this, and we're going to solve we're going to solve some equation of motion stuff. All right, see you in the next one.